Hey,
Hello.
Luca.
Hey, how are you doing?
Good, good.
Yeah, the school is almost over. So it's great, except that it doesn't make a difference. Well, it does make a difference because then you have kids and they need to entertain themselves. But apart from this, the good old times where you had like a couple months off are not, not anymore for us. But
Yeah,
we're keeping ourselves entertained otherwise, which is there are a few deadlines coming up. One is the uh, PyTorch conference abstract deadline, which is very nice. So please, to other people eventually watching us, submit a talk to PyTorch conference. It's going to be pretty huge.
yeah,
I know because, last year was already large and this year is going to be even larger. And yeah, well, have the representation from VLLM and deep speed that entered the PyTorch Foundation. So it's pretty cool. And Thunder will submit an abstract as well. Hopefully, we'll get selected.
yeah.
Yeah, so that's good. What else? What else? I think today it would be nice to talk a bit about something that is going to be more and more interesting as new hardware architectures come
Yeah.
and be are deployed. Like we talked about Blackwell supporting FP8 and another flavor of FP8, MX FP8 and FP6, FP4, and all these things are not just supported out of the box usually. And so you need to take your model and do something to it so that it can use all these features. And NVIDIA published a library that is called TransformerEngine that provides a few specialized layers for these for these data types, and and they're not just like your usual bfloat 16 because they have more stuff, right? They you need to like they have such a small number of bits that the bits alone are not enough to represent numbers in a way that you can use them. And so they have some state attached to them. And this complicates everything.
Yeah. You need to like keep scaling factors around and stuff like that.
Yeah. I think
Uh,
we talked about quantization a while back, and this kind of is a flavor of that. As you reduce the number of bits, you need to make a trade-off between how wide and where your numbers that you can represent and how spaced they are because you have like kind of fewer points on the line on the number line that you can position your numbers that are going to be a few and not cover the whole thing. So what does that mean for a model? Like if I want to adopt that in my model, what do I need to do? Sometimes I just need to replace a linear layer. But then if I do that, I just say, okay, replace my linear layer with this. Then you kind of preclude yourself to do other things to the same linear layer. Because like, say you want to shard or you want to do tensor parallelism and so on, you still need to do things to linear layers. So say you say, okay, I have my standard linear layer. I replace it with a TransformerEngine linear layer. And now my model uses TransformerEngine and whatever TransformerEngine supports, but I cannot do more things to it. It's like monkey patching. When you monkey patch, you replace something with something else. But if you then want to re-monkey patch that, you will basically kick the other thing off and replace out and then replace the thing with the thing you're monkey patching again. So it's not composable. And since we are all about composition, then we would like to make TransformerEngine something that you can apply through a transform so that then you can also work around, in other transform, you can work around that thing and make sure that you can also apply like some sort of distributed other things, checkpointing, offloading, whatever. So today we're going to cover a bit of like TransformerEngine in Thunder and take a look at the advantages that it brings in terms of performance and memory utilization. And maybe we can take also a look at the transform itself, like what does it do and so on. I think it's
so if you remember well, I think it's the 20th session, which was in January from Bergamo, where we talked about FP8 and and then of course this week was a crazy week because on Monday the PR with the Autograt transform landed, but then there was a problem with the checkpointing, which is like recomputing the forward during the backward or parts of the forward. And so that was not so good because, when other people find or a big change disturbs other people, that's always not so nice. But
sometimes, big changes come with disturbances. Yeah. Okay, you can't go in there with an elephant and hope that every piece of furniture will stay at its place. But right now, the AutoDiff is a transform, and it's like a massive step ahead. So props to that. And
So FP8 transformer engine.
Yeah. So I would say let's take a look at the transform, the FP8, the TransformerEngine transform itself, because I think it's. Do you want to share yourself or?
Either you can or I can.
Yeah, well, maybe it's better if you do it because I'm a bit of in a pickle here with respect to the screen for some reason.
So let me share. So this morning my keyboard stopped working, but happily it started working again. That was like a bit of a scary moment.
Mechanical?
The laptop one. So.
Oh wow, that's not good.
And somehow, I don't know, the key got stuck, and then I tried to take it apart and all that. Okay, so here's the TransformerEngine documentation.
Yeah.
And of course, the goal would be to have redo this in Thunder, right? Without modifying the model, attach all these things. And that's how they see TransformerEngine. I don't know if the blue part is the TransformerEngine or the orange or both. But that being as it is, we can.
So there was a colleague from NVIDIA who's working on TransformerEngine, Ricardo, and he did contribute a new backend for TransformerEngine, which is kind of the excuse why we're using to talk about TransformerEngine here. Before we were doing more just replace the linear layer, but that had some challenges. Do we want to talk about the challenges that we had before in the previous incarnation of this?
Well, so there are two parts, right? One part is that I guess Thunder was one of the first things to use TransformerEngine the way we did. And so the old way of how the TransformerEngine API worked was a bit tricky because of the state that you mentioned that TransformerEngine or the quantization needs to keep, and so TransformerEngine needs to keep it. Basically, we ended up using TransformerEngine in some undocumented ways. And so the NVIDIA colleagues chatted with the TransformerEngine people, and we got to talk with them too for a little bit, which is awesome, right? They're people and have thought very deeply about these things. And so now there's a TransformerEngine version 2. And now there's a TransformerEngine version 2 executor as well. And you need a transform that comes to it. Right now, what it does is basically it fixes up, it adds the state to the bound symbols. But further down the road, I guess that we would want to also fuse some of the operations if we can, because TransformerEngine can basically, it can also handle the entire block, but you need to give it to them in one thing. And so I guess this will be also here the more extensible way. So let's see what the implementation, the transform does. So remember the executors, they have this execution transform, which allows you to say, well, yeah, if you want to run this thing, you can run these bits, and this will be how you can redirect like one linear layer into some bespoke symbols. And there also was the gradient transform for derivatives that also was featured in the autograph thing that we just mentioned. But so for more complex operations, for example, dealing with several bound symbols at once or doing bound symbols things, this needs to look at the entire trace at one time. And so for this, you need to have the transforms. And at this point, this uses the post-optimization entry point. So this is not yet the fusion. That would probably be a lot earlier, but or somewhat earlier. But so here is the TransformerEngine transform, and what it does, it goes over all the bound symbols, and then it looks at the transformer, whether there is operations about the recipes for the TransformerEngine, and this encodes how TransformerEngine encodes numbers. And then if it finds them, I think it attaches them to all of the bound symbols, and that's basically what it does. And it also modifies the safe for backwards, because you need to move the state around a bit more explicitly. Maybe we can also look at a trace that uses TransformerEngine, right?
Yeah. The principle is that if the state is buried inside your linear and you don't have access to it, then you cannot reason about like saving computations, blah blah blah. Because if you reapply the same computation and you do it on top of a state that is not the right one, then you cannot redo exactly the same computation, because a matrix will contain numbers, but these numbers are only contextualized in actual numbers when you pair them to the scaling factors. And so if you perform a computation and the scaling factor changes, and then you reperform the computation again, but the scaling factors have changed because it's a stateful thing, then you haven't re-executed the same operation, because the scaling factors are not the same. And so having the scaling factors be exposed to the trace and be inserted in the trace in such a way that we can reason about them, that makes thinking about like saving or recomputing and saving memory by recomputing something that is possible to handle at the transform level, essentially.
Okay, this was supposed to be let's just have a mini trace with that. but maybe we just look at the numbers first and then the how. Okay, so I prepared this, and there is a thing in Thunder, which is the Thunder benchmarks repository, and we didn't talk about it too much, but it basically gives a few things where we're interested in the performance, and also our NVIDIA colleagues measure performance with this. And we can do a little training of a Llama 3 8 billion model here, or some other ones. And we will use 8 GPUs. I'm on an H100 here. And today I'm doing the full RISC thing, and I have an interruptible studio. But so far, it has been like pretty good. And so if we run the full thing, the normal thing, this is without TransformerEngine, and you see that Thunder needs to compile itself, and this is one of the things where we will look into making it faster, and it takes a while. And while this happens, I can see that I can now import Thunder and have a mini model here. Torch, and then I need torch, right? Torch and then sequential, and torch and then linear. And we probably need like multiple of something dimensions for TransformerEngine to do its magic, but that shouldn't be a problem. And let's instantiate it on CUDA directly and see if we can compile it with TransformerEngine, right? We can also have an input, random vector 16 times 2048. And so the compiled model is ThunderJIT and of the model, and we need the transform. So torch executors, no, Thunder executors. TransformerEngine X V2. It's not like there yet. So what did I do? So I need the transform.
And this will be nicely packaged up into a recipe. So we don't have to do so much typing.
Yeah, I look forward to that.
Yeah.
And we need the executor too, right? Executor.
Yeah, this is one of the cases we were mentioning before where we need a transform to do certain things, and then we need to register the executor that will take up whatever bound symbols to just execute them. So our kind of dispatching mechanism here. And so, one is tight connected to the other, and we will make it, we'll slap in the same in the same recipe. But if you use the ThunderJIT endpoint, you're going to have to specify both. Maybe we'll make it simpler for even in this case. But.
Yeah, right. And obviously, I'll be the first to profit from that, right?
Yeah. Yeah.
Okay, so now we have JITted our model, and we can call it just like we always do. And in the meantime, this ran through, and you see here there's a few key statistics, and maybe the most important things is the average iteration time and the memory used, and you see that's 885-ish milliseconds per iteration and 70 gigabytes. And now this is a bit messy, but it gets the job done. So if I add here TransformerEngine, and this is not spell checked in any way, so you need to know exactly what you're typing.
And this is this was in bfloat 16 mixed precision by default?
Yes. So that's the default, I guess. And now this will be with FP8. And let's see how that goes.
Yeah.
And while we're doing this, let's look here. There's a Kublas status not supported. That's not good. I don't know what's up with the CUDA installation here that I have. So pip list Kublas, pip install Kublas 212, and let's just upgrade it. But yeah. At any rate, we could look at the traces even if the execution fails, right?
Yeah, exactly.
But it's not as satisfying. But
well,
for the good stuff, we have this, which runs the real model, right? And so let's look at the traces. Thunder traces.
Which is one of the nice things where you can look at the traces without running, so on your laptop.
Yeah, even when it's failing, you can see it. Yeah. And you see here what the new version does is it explicitly gets the scales and treats those and the quantizers, and this is treated as explicit objects.
Now, this is interesting because if you go up to the comment there, the first thing would have been a linear, right? So that when it says 3 lines up, you have a linear, and there's a bunch of things when you go to FP8 that needs to happen. One is, what is the recipe? The other one is like there's a state associated to this linear, and then you make it explicit, so you can basically then later on, if you want to replay this exact execution, then what you're going to do is take the input weights and the state and the inputs, and that will replay exactly the same computation. Otherwise, if you don't have the state, you don't get a hold of the state, and you just like blindly use the linear from TransformerEngine, you will get a different result. That's the take-home message, because the state has evolved into something else. Every time you use it, the state gets updated, right? And so, and why am I talking about redoing the computation? Because we talked about it, computation and memory. You can use less memory if you then in the backward instead of like just running the backward of this operation, you also recompute this operation, then run the backward again. And this is something that you need to do for significant workloads. And that's why it's important to say, okay, now I don't care what happened before me. I'm just going to replay this exact computation the way it had happened in the forward. And that's why it's so important to get a hold on the state. And here we have an explicit representation of exactly this phenomenon.
Right. And of course, in the future, we would like to have one transformer engine thing, and here it goes to the quantized version here, and then goes back. And of course, it would be cool to just have that in one go. But now you have this in the forward, and then in the backward, there's similar things again, right? There's the quantizers here. It's not like the type representation could be nicer. But then you have the linear backward that basically gets the scale information. There's an update to the scale too. And then it goes on here. And so let's see what that meant. So remember that took 75 gigabytes of memory here. And we're not saving a whole lot of memory, but part of that is that we keep the weights around for everything. So this is very limited where we actually save memory. But it got quite a bit faster. So we're at a little shy of 700 milliseconds per iteration instead of 800.
Almost 9, 880, 890.
So that's more than 20% speed up, almost a quarter, and that's quite a bit, right?
Yeah, exactly. And like traditionally, it's been hard to train using in a very stable way using FP8. And particularly in Hopper, if you read the DeepSeek R1 papers, and also there was a more recent one by DeepSeek, where we kind of discussed high level the innovations that they brought. And one of the things was, in fact, the stable FP8 training. And you would have to use a very specific recipe that they suggest and so on. But if you move to Blackwell, then there's a numerical type that is called MX FP8, which is always an FP8. And Thomas has disappeared. Sorry about that. It's an FP8, but the scaling factor doesn't apply to rows or columns. It applies to blocks. And that is a much more stable way of reducing precision in practice. And apparently you can get FP8 training kind of worry-free. And yes, and then we talked about FP6 as before. Right now, I don't think there are good recipes for training in FP4, for example. It's more something that you would use for inference, but the gist of the thing doesn't change. And well, yeah, we have Thomas back. Yeah, I was saying things about you, and
yeah, sorry about that. At some point, I will learn that stop sharing and leave is not the same.
In German, they are kind of the same word, but yeah. And I was basically talking about MX FP8 in Blackwell. That is where you get scaling factors that are like more localized, and so it's a more of a submatrix level, and that makes training a lot more stable. So you don't have to apply the tricks that DeepSeek found out, unless you have Hopper, in which case you cannot apply the same tricks because there's no hardware acceleration for MX FP8 formats. And then FP4, FP6 have not been reported to be things that you should use during training. But they're all supported by TransformerEngine. So the transformations that we saw would apply to all of these things.
Yeah,
yeah.
Of course, at some point we should like get really deep into all the various TE calls that we saw, but maybe we leave that for the next time.
Absolutely. Okay.
The next one.
Thanks, Thomas, for the update. And yeah.
Yeah. Thanks, Luca.
Have fun. And thank you.
Always fun.
Yeah. Same. Bye-bye. Thanks.